It's time to learn about the Pythagorean identity, and we're going to see what it looks like with and without reciprocal trig functions. So make sure you've watched the video on reciprocal trig functions prior to this. We look at our wonderful device, the unit circle, and oops, bit rough, sorry. So unit circle of sorts. We have our axes. I meant to turn that into purple. It's come out still the wrong color. Doesn't really matter. Okay, so with the unit circle, if we look at quadrant 1, for example, and we have our radius arm or radial vector in green there, which conveniently is 1, we know that we have components and a position here correspondingly on the circle that it traces out. Point P with coordinates x, y. Putting in those components, we have the x ordinate, or in other words, the x component along there. And we have vertically y corresponding with that y there. We can write that in there. Additionally, we have a right angle, so it's a right angle triangle, and also we have an angle theta. Now you've seen, if you studied the unit circle, which you must have to watch this video, you would have seen all that by now. You would also know some things about sine and cos. You would know that basically cos theta on a unit circle is the x coordinate or the x component, and for any given angle sine theta is the y, so cos is the x, sine is the y. What about if we use Pythagoras' theorem on the little triangle? So we would have x squared plus y squared equals 1. You can see that there. And if we have this substitution in for x, that would be cos theta all squared, and correspondingly for sine and y, sine theta all squared, that equals 1. From hopefully the previous video you've watched, or your previous knowledge, that can be written as cos squared theta plus sine squared theta equals 1. And that essentially is the Pythagorean identity right there. So whenever you have sine squared of a particular value plus cos squared of the particular value, it equals 1. There are two other forms of the Pythagorean identity that you will see, and the second one is like this: 1 plus tan squared theta equals sec squared theta. Now remember, it shouldn't be a surprise, even though you might not have seen it before. Sec squared theta is sec theta all squared, if you've watched the previous videos that correspond to this one. Also, cot squared theta plus 1 equals cosec squared theta. They're the three forms. Now they're not just magic, they actually occur. If you start here, you can get the other two forms. If you start for form 2, 1 plus tan squared theta, how do we get this first term cos squared theta to become 1? What do we have to divide by? Well, let's have a look. I'll change color. We might change to this color. So if we divide through every term by the same thing, I'm going to choose cos squared. So if we divide everything through by cos squared theta, so cos squared theta over cos squared theta, then we have sine squared theta over cos squared theta, and we have 1 over cos squared theta. That will come out as 1. That will come out as sine theta on cos theta all squared using index laws, and this will come out as 1 over cos theta all squared, again using index laws, and that would be 1 plus, that should have been a squared there. Okay, so sine squared theta over cos squared theta is sine theta all squared over cos theta all squared, which is sine theta over cos theta all squared, all index laws. Okay, so that will be tan theta all squared, or in other words tan squared theta. This is sec theta all squared, or in other words sec squared theta. So it's a little proof, a little semi-formal proof there. For this one, how do we get that one? Well, we start with the same thing. I'm going to switch colors. Cos squared theta plus sine squared theta equals 1. Now, the hint to me is there. If we divide everything through by sine squared theta. Alright, so I'll do it for the first term as well. And this is a slightly rushed proof. You could probably flesh it out a little bit more than that, but this is basically a formal justification. So we're ready to roll. We've got, obviously, this term here will be 1. That's good. Now 1 over sine squared theta is 1 over sine, 1 squared over sine squared theta, which is 1 over sine theta all squared. This one here on the left is cos theta over sine theta all squared. This is all index laws, and that's the inverse of tan, which is or the reciprocal of tan, I should say, which is cot, and it's squared, so it's cot squared theta plus 1. This one is cosec theta. It's cosec theta that has been squared, so it's cosec squared theta. Okay, almost a proof. Just probably we just need a little bit of annotation and an RTP up here, and just a little bit more formality. But that's basically why they work. A couple of quick examples. If we have to find cos x, given that cosec x is 7 on 4, we can use all the stuff we've just established above. So if cosec x equals 7 on 4, that's the reciprocal of sine x, and sine x would be the reciprocal of 7/4, which is 4/7. So if we put that in the Pythagorean theorem, that would be sine squared x plus cos squared x equals 1. So if sine x is 4/7, sine squared x is 16 on 49. And therefore we have, I'm missing a little x there, 16 on 49 plus cos squared x equals 1. So cos squared x is 1 minus sine squared x. Always be prepared to do that. So it's 1 minus 16 on 49, or in other words 49 minus 16 on 49. So cos squared x is 33 on 49. So cos x is the square root of that, but it's the positive and negative, because when you take the square root, there are positive and negative values unless there are limitations, and it would be plus or minus root 39 over 7 using your surds or your index law. Oh, sorry, wait on 33. That was 33. All right, so it was 33 Let me just quickly tidy. Alright, so don't know where I got the 9 from, probably from the line below it, 33. There we go. Last example, we've got given that sec x is negative 3 over 2 and we have a restricted domain. So we're only talking between inclusive pi on 2 and pi, so you can see that shaded in the unit circle there in brown. We have to find sine x. Okay, so we start similarly, so sec x is negative 3 on 2, so that means that we can use the reciprocal of that. So cos x is the reciprocal of 3 on 2, negative. So it's negative 2/3. Okay, so cos squared x is the square of that. Now it's a positive 4/9. And we use the rearrangement of the Pythagorean theorem, identity I should say, as such. You can see that there. And 4/9. Oh, I've rearranged it wrong. That's better. Okay, so we have 1 minus 4/9, which is 5/9. So sine squared x is 5/9. So sine x would be the square root of that, which is root 5 over 3, plus or minus. Now, restricted domain, we've basically, from your other math methods that you would have learnt, year 10 and 11, we are only looking for sine as a positive, so no negatives. So basically, it's the positive answer only. So, quadrant 2 is basically mean positive only for sine, so sine x is positive root 5 on 3.